All right, I'm going to start the recording. Okay, so today we're going to talk about greedy algorithms. And so basically what a greedy algorithm is like, it's an algorithm where you're trying to optimize for a certain quality. And at each point in the algorithm, when you can make a decision, you make the algorithm that at that best point is the best decision for you. So for example, if you wanted to so here we're talking about a road trip. Okay, so where we can make several stops during our road trip, but we can't travel at night, so we can travel a certain distance every day, and we're trying to spend the least amount of days possible to get to our final destination. And so what we have here is like a greedy solution, where basically at each point we make the decision to minimize the amount of nights we need. So we maximize like the amount of travel in every given day. And what we do is by for every point that we stop, we see if we can make the next point before sundown. So we basically travel to the last possible stop we can travel to before the sun starts the next day. And so we assume that the distance between any two stops can be covered in a day. So assume, let's say we can travel d miles in a day. Okay, and we want to, so d is like less than or equal to the distance. Oh, sorry. It's greater than or equal to the distance between any two stops. Let's call it stop I and stop I plus 1. Okay, so what we have to show here is that our argument is that this algorithm is optimal, basically, that we can't do any better than this. And so the way we're going to do this, okay, in general for greedy algorithms is we're going to look at the solution that our greedy algorithm outputs, and we're going to look at the the solution that our optimum solution would be, right? So we look at the optimal possible solution, and we argue that the greedy algorithm is like strictly better. Okay, so formally, what we want to show so we're going to say the greedy algorithm makes stops at, so on the first day we make a stop at P1, P2. The second day we make a stop at P2. Third day we make a stop at P3, and then on the mth day we make a stop at PM. And the optimum solution, the optimum in terms of fewest number of nights, we're going to stop at Q1 on the first day, okay, Q2 on the second day, and so on until we stop at Q sub k on the final day. Okay, so here we know that, what do we know about what do we know about this? We know that k is less than or equal to m. Why is that? Because, well, this is the optimum solution, so it has to have at most the number of nights spent as any other solution, especially one output by an algorithm. We want to show, okay, that's what WTS stands for. We want to show that k is equal to m. But first, what we're going to show, okay, is that P sub I. So let's say take the solutions, call it x of P sub I. So what this means is distance of p sub I from start. So in the ith night, we stop at some sub p sub I, which is x of p sub I distance away from the beginning. Okay. So if p sub I is 100 miles from the start, right? We've traveled 100 miles on the first day, then x of p sub 1 would be 100. Okay, we want to show that we travel further, or at least as far, on the greedy solution as we do for the optimum solution. For every I that this is the case, at least for the first k i's. And then we also want to show that we don't spend any extra nights, okay? Also, we want to show that we don't spend any extra days traveling. So how can we express this in terms of the variables? We know that we spend at least as many nights as the optimum solution. How do we say we spend at most as many nights? Anyone want to say something in chat or unmute themselves and say something, or just
Why do we have to show that? Isn't that just the definition of the greedy algorithm? Is that you're always gonna pick the longest route?
well, it's certainly true on the first day, okay? But like the idea is like that's going to end up being the argument, right? So we're going to show it by, okay, I won't spoil anything, but like the idea is on the first day you do travel longer, but like what if after the first day, okay, you're left with a long distance and you can't travel as much on the second day, for example.
Oh, okay.
And so yeah, go ahead.
This chi x function, could you explain again what this function is doing?
Yeah, so p sub I is like a distant, is like a stop, okay? So p sub I is the stop that we stop driving at on the ith day. Okay?
Yeah.
X of p sub I is the distance. So p sub I is not a number, it's like a label.
Yeah.
X of p sub I
is that the distance to the start or the distance to the previous stop?
It's the distance to the start.
Okay.
Yeah, good question. So yeah, okay. So I'll just answer my previous question. So we know that the optimum has at most as many nights. How do we show that the greedy solution has at most as many nights as the optimum, thus showing that it's also optimum in terms of our like cost function. We also want to show that M is at most as much as K. Okay, that is we don't spend more nights because of our greedy solution. Okay. Any questions here about like what we want to show? Okay, so here's the idea, okay? So we, on the first night, it's clear, right? Does it make sense that x of p sub 1 we know that for x of p sub 1, we travel further, or at least as far as x of q sub 1. Let me make this more clear. Does this make sense? Well, this follows immediately from the definition of what p sub 1 is. We travel as far as we can until we have to make a stop. Okay, we don't stop abruptly or previously, like just before we reach the last possible stop. We stop at the last possible stop before night. Okay, and so this makes sense. And so the idea is we're going to use the truth of this along with the structure of our greedy algorithm to show that for each I, x of p sub I is greater than or equal to x of q sub I, and then we're going to show this. So what proof technique do you think we're going to need to show this first part over here? Anyone? We're awfully quiet today. give you a hint. It starts with an IND. Whatever. It's induction. Okay. So we're gonna show that for every day, right? If my current stop is further ahead than the optimal stop, and then like one day of travel, within one day of travel, like I can't get further in my optimum solution than my greedy algorithm. So that is on day I, if my greedy solution stops at least as far as my optimal solution, then on day I+1, that is also the case. Okay. So if that is the case, that for each like p sub 1, a distance of p sub 1 is greater than distance of q sub 1, distance of p sub 2 is greater than distance of q sub 2, and so on and so forth, we have to argue then that m is at most as much as k. Okay. And so think about how you might argue that as well. So I'll zoom out and then I'll give you all like 10 minutes to work on this or something. Okay. Feel free to ask any questions as they arise. Okay, so I'm gonna get you all started for a bit, just in case you're stuck. Like I said, we're gonna do a proof by induction, right? So what are we going to induct on? By induction, we're gonna show for any I, oops, okay, x of p sub I, which is the distance of the ith stop in our greedy algorithm from the starting point, is at least as big as x of q sub I. And so what is our base case over here? Well, our base case is the first stop, I is equal to 1. So we want to show that x of p sub 1 is greater than or equal to x of q sub 1. And we argued this on the previous page, but I'm just going to reiterate it just for someone who might have not gotten it the first time. So x of p sub 1 is how far we travel on the first day in the greedy solution. So we travel as far as we can before like the next stop. So like we stop at the stop that like okay, how can I explain this? We travel as far as we can without going to a stop that would require us to travel in the night. Okay, so if there is a stop that requires us to travel at nighttime, we don't go there and we stop at the stop that's one before. Okay. So the idea here is x of p sub 1 is as big as any stop on day 1 could be. Assume it was bigger, right? If it was any bigger, then we'd have to stop or drive during the night, which contradicts like the conditions in our problem. So certainly it must be true that x of p sub 1 is greater than x of q sub 1. Any questions about this base case?
Sorry, could you say that again?
Yeah, sure thing. So x of p sub 1 has to be greater than or equal to x of q sub 1. Why is that? It's because if x of q sub 1 was greater, okay, it would require us to travel during night. Why is that? Because p sub 1 is the last stop that does not require nighttime travel. In other words, let's say this is how far we can travel. Let's say we can travel a distance of d, or let me draw it like this. So let's say we have like, this is our road, okay, and we can travel a distance of d miles every day. Okay, let me change my color here. Okay, so we have a bunch of stops along the road. So this is going to be p sub 1, right? Because it's the last stop that we can travel within d miles of leaving the starting point. Okay, this is the starting point. This is the last spot we can travel to, right? Like right here. And if q sub 1 was greater, it would have to be here or further. But we noticed that like, since there's a gap in the amount of time we can travel in a day and the distance to this one, we'd have to travel in the night if x of q sub 1 was greater. So it must be the case that x of p sub 1 is at least as big. Okay, so so now let's talk about the inductive hypothesis. For some fixed j, x of p sub j is greater than or equal to x of q sub j. That's our inductive hypothesis. Okay, and so our inductive step is going to be we want to show that, what do we want to show? We want to show that this is true for the case of j plus 1. So x of p sub j plus 1 is greater than or equal to x of q sub j plus 1. Okay. Now how might we show this? Okay, so let's draw a picture. By the way, proof by picture is not a valid method of proof, okay? But pictures will often help in making things more clear. So let's say this is, for the sake of argument, this is stop p sub I. And we know that stop q sub I is just a bit behind, or is behind or equal to p sub I, okay, in distance. And so now let's say we travel to p sub I plus 1, okay? And basically, this is a distance d, okay? Actually, sorry, let's instead of p sub I plus 1, let's say this is q sub I plus 1. Okay? Oh, sorry, I used j instead of I. My apologies, guys. Okay, so what is this diagram over here? This diagram is saying that in the optimal solution, okay, I travel from q sub j on night j to q sub j plus 1 on night j plus 1, or before night j plus 1, really. And q sub j is at most d away from q sub j plus 1. Why is this? Because d is as far as I can travel in a given day. I don't want to leak over to the night, so we know that this is true. Okay. What else do we know is true? We know from the induction hypothesis that x of p sub I is less than or equal to, pardon me. Sorry, I'm making tons of mistakes today. X of p sub j is greater than or equal to x of q sub j, right? Why is this? It's just from the induction hypothesis. This is further along. Okay. And so combining these two facts, okay, we're going to get that x of q sub j plus 1, so the optimum spot, or it's like some optimum spot on j plus 1, is at most is also at most d far from p sub j. Okay, this is something that we want to show.
So are you writing something down right now? Oh.
I am. Are you not able to see it?
We only see the two
bullet points.
Yeah.
Oh, that's weird. It says I'm screen sharing. Like, can you hear me okay? Is there any lag? Okay. I will stop sharing and restart, okay? I'm sorry about that. Let's start sharing again. Where's the button?
Wait, so basically, is it proof that like since of x of qj plus 1 minus x of qj is less than equals to d, and also that p of j is greater than equals to q of j, it's like saying since q of j was before like is p of j, since the distance d can't be like since q of j plus 1 can't be at a distance that's greater than d, it's like saying if you add the maximum distance d, then q of j plus 1 has to be greater than p of j plus 1 has to be greater than q of j plus 1.
Exactly. Yeah, okay, that's awesome. What I'm going to end up showing. Okay. Yeah. Okay. I had to use my cable. For some reason, my AirPlay is just, oh, that's unfortunate, but I don't care. So, okay. For some reason, my AirPlay is not working, but whatever. I have to figure that out. So this is what I wrote down while my screen was not sharing, okay? We want to show that the distance between the optimum j+1th night stop and the greedy jth day stop is at most d, okay? What does this mean? Why does this show that we're done? Well, it shows that if we stop at p sub j in our greedy solution, then we are able to stop at q sub j+1, at least that far, okay? We might even stop a bit further within that d distance from p sub j, but we're showing that we're at least able to stop at something that is at most d far, or from our solution, right? In other words, we're able to stop at least as far as we are on the j+1th day of the optimum. Okay, if we show this, okay, then we show, well, let's get there when we get there, okay? Maybe perhaps if I show it another way, it'll make more sense. So how are we going to show this? Well, it makes sense intuitively. P sub j is further up than q sub j, and q sub j+1 is further up than, say, both of them. Then the distance from q sub j+1 to p sub j, okay, q sub j+1 to p sub j should be at most the distance from q sub j+1 to q sub j, right? So therefore, another way to say this, I suppose, is we can rewrite this as x sub q sub j+1 is less than or equal to x sub q sub j plus d. And now x sub q sub j is less than or equal to x sub p sub j. Okay, so we substitute. I hope you all can see my mouse. You can see my mouse, right? This over here.
Yeah, we can see the mouse.
Okay, fantastic. That would be really awkward if you couldn't. So x sub p sub j is at least as far as x sub q sub j. So this is at most x sub p sub j plus d. And then so rewriting this, we have x sub q sub j+1 minus x sub p sub j is at most d. Okay. And with that in mind, we've shown this. And so what else do we know? Right? We know that we can travel up to d far away from x of p sub j, or sorry, from p sub j, right? We can travel d miles towards the end. And so we will pass q sub j +1 along the way because it's at most d far away. So we'll pass it. So we'll stop at least there, right? So we won't be forced to stop, say, here, because there is a stop that we can reach within the same day that is further away. Okay. So therefore, what we've shown is that our stopping point in our greedy solution on the j+1th day is at most the stopping, or at least the stopping point of the optimum. Okay. And we've shown that, therefore, by induction, we've shown that this is true. Okay, we've shown that for any particular day, that the stopping point of the greedy is at least as far away as the stopping point of the optimum. Any questions about this proof?
I had a question more so just about, like, I guess, induction as a whole.
Yeah, sure thing.
So I just wanted to clarify something about the inductive hypothesis. So I saw that you said for some fixed j. In one of my previous classes, the professor usually delineated in what range j exists. Like j is greater than 1 and less than n or something. Is that necessary? Or because I noticed Professor Frage kind of doesn't do that a ton either. Is that
Yeah, so good point. I suppose I was just kind of being like lazy. And so it's not really necessary, but I think sometimes it is. I mean, I can't think of a case off the top of my head where it's like absolutely necessary, but here like well, so first of all, okay, uh q goes from like q sub 1 to q sub k. So there are at most like k of them. So between 1 and k. Actually, it should be k minus 1 because q sub k plus 1 does not exist.
Mhm.
Well, yeah. So I guess you could do k. Should think. Just for any arbitrary fixed k in this range, assume that this is the case. Yeah, k minus 1 because then we do k plus 1 over here. Okay, so pardon me. It's not absolutely necessary. I at least when I'm grading y'all's assignments, which I do, by the way, I'm in charge of grading some of them. I like look for mostly like big picture stuff. Like if you have most of the proof is correct, like, and you make like a tiny mistake, like for example, you write I instead of J, I will deduct 0 points for something like that. Like unless the mistake indicates to me that you don't understand the problem, or you don't understand the solution, I will generally not deduct points for small mistakes. However, I will say I am pretty harsh about deducting points for like not understanding the problem. So I would say like don't stress out too much about the little details, but it is probably a good habit to start building them just in case that not putting this would result in something that is incorrect. Okay. In particular, saying something like this is a bit iffy because we haven't shown that q sub m even exists. We know that the optimum solution has like at most or fewer nights than the greedy solution. So q sub m might not even exist. Okay. So you do want to be a little bit careful, but overall it's not that big picture. So good question. Okay. All right. So where was I? Okay, so any other questions about the induction proof?
Sorry, I kind of had another one that I was like hoping to get clarification on.
Don't apologize for asking a question. Go ahead.
Yeah, so I saw that in like that, like you've been using like without loss of generality like a couple times.
Uh-huh.
Um, so do you have any examples of where like without loss of generality is like, or like cases in which without loss of generality would be like inaccurate? Because like I feel like it's like still kind of gray, like where I should and shouldn't use it.
Yeah, sure thing. So okay, well, off the top of my head. Okay, so I guess without loss of generality would be incorrect wherever there isn't symmetry in a problem. So sorry, it is tougher for me to think of a situation right now, but like I guess I've thought of an like once we're done with this, I thought of like, so I'm gonna give you all the option between like me talking for one of the previous like topics or giving you another greedy algorithm problem and demonstrating like some new kind of proof. So I'll show you an example there where without loss of generality like works and why it works, but I'll have to get back to you on an example where it doesn't. There's probably examples I could find on the internet. So while you're working on this, I'll look that up. Okay. So I'll get back to you on that. Any questions about any other questions about this? Okay. Oh yeah, there's a question in the chat. Oh, okay. Yeah. So all right. So now we have to show.
Also, if you have time, could you go over or at least like kind of go through question 3 of the homework? Is that allowed or?
Yeah, sure. Well, actually, in that case, could we do that at office hours? Because I'd prefer to like, we could like find a time. So I don't have office hours this week because I'm moving my time because it conflicts with one of my research meetings. But I put my email on Piazza, so if you can just email me, we can set something up.
Okay.
Okay, yeah. So, okay, now we want to show that M, okay, which is the number of days in the greedy solution, tried to draw in white, okay, is at most the number of days in the optimum solution, okay? So we want to show that M is at most equal to K. So what do we know? Okay, we know that K is K is K is the number of days in the optimum. So we know that like K is at most equal to M. We can do this by contradiction, I suppose. But another way we can do this is by showing that x of p sub m is equal to x of p sub k. Because that shows that between the kth day, which is when our optimum solution stops, okay, and the mth day, which is when our greedy solution stops, we don't travel at all. So we might as well just end it on the kth day. So how can we show this? Well, we know that x of p sub k is less than or equal to x of p sub m. Okay, because k is less than or equal to m, so we have to travel further along the line. And p sub m is the ending spot, right? P sub m is the final stop in the trip, so it must equal x of q sub k. Does everyone see this? So remember here that p sub m is our stopping point with our greedy, and q sub k is our stopping point with the optimum, and they both must be the same because there's only one stopping point. Okay, so this is true, and by our previous argument, we know that x of q sub I for any I is less than or equal to x of p sub I, so this is less than or equal to x of p sub k. So we've shown that x of p sub m is at most or at least equal to x of p sub k, and at most equal to x of p sub k. Therefore, it must be equal to x of p sub k. Therefore, by the kth day, we're already at our stopping point in the greedy solution. There is no more distance to travel. So we might as well just end it on the kth day. Any extra days don't give us anything. Okay. So now that we've shown this, our argument is done. Any questions about that argument just now? Okay. So if you do have any questions, just feel free to put them in the chat. Okay. So I guess a moral here is that greedy algorithms are generally straightforward to describe, but like somewhat difficult to analyze. Why is this? It's because it's because greedy algorithms, like the description is pretty run of the mill. You like at each point you make this optimum decision, okay? But proving that optimum decision is correct, like there's several optimum decisions you could make, right? So proving that that one particular heuristic to optimize, in this case, it was the furthest distance you could travel without like going during the night, or the furthest stop you could travel without traveling during the night. Showing that that's optimum, that requires a bit more work. So generally, like the solution here, okay, so I'll add another moral. to prove greedy algorithms correctness, so to prove that greedy algorithms are correct, so you can compare directly to optimum and make arguments that way. So why is that useful? Well, you're comparing. So here what we did, right, was we compared each like stopping point to the optimum stopping point. And we argued that the greedy algorithm was at least as good. And the way we were able to do that is because we had a very particular structure on our greedy solutions. That is, each of these p's of I were pretty well defined in terms of what the previous ones were. We travel at most d distance, and the final stopping point before that d distance is up is going to be our stopping point. Okay. And based on that, we are able to argue optimality. And so that's generally how proving things for greedy algorithms is going to be. Okay, you compare directly to the optimum and you use the structure that you get from the algorithm being greedy to show correctness. Okay. Any questions about that moral? Okay, so I have another practice problem for y'all. But I'm also going to give you all the option of like, if you want me to talk about one topic from a previous discussion, I'm more than happy to do that as well. So I thought of a greedy problem as well, and I can also like just talk about any like other topic that we've covered in class. Do we have any suggestions about what we want to do? Okay, so greedy. Okay, so we want to talk about greedy. Okay, so just to be sure, I want to make sure that I'm not covering something that's going to be on the homework. Okay. Okay, so the problem I have for greedy algorithms is called the knapsack problem. Okay, so we're going to call this like the fractional knapsack. I wonder if this is a little ambitious. We probably won't get to the entire solution now, but I'll hint towards the solution, and then feel free to like email me or something with a proposed solution to this, and I will be more than happy to check it for you. So the fractional knapsack problem, okay? We have k items. Each has, okay, we have k item sounds discrete. Let's say we have k like powders. Okay, wait, that sounds kind of sus. K spices, why not? K spices. And so with spices, you can take any fraction of them, okay? Each has q sub k is the quantity in like, in what your favorite measuring units. In like, let's say we have grams. Okay, no, this is America in ounces, whatever. Okay, so Q is the quantity of each spice that you have. Okay, P sub K is the price of the spice in dollars per ounce. So for example, if I have like cinnamon, if I have 5 ounces of cinnamon, which sells for like $3 per ounce, that's some expensive cinnamon, but that's Q sub K would be 5 because I have 5 ounces of it, and P sub K would be 3 because I get $3 for every ounce of cinnamon that I sell. Okay. You also have Okay, you also have a knapsack to contain these spices. And a knapsack is basically like a fancy, maybe it's like British. It's a name for a backpack where you're putting your spices or you're putting your items. Okay, and you can take any fraction of any amount of spice. So for Q sub k, it's like 5 ounces. I can take like 3.73 or whatever ounces. Okay, with so the knapsack has capacity M in ounces. Okay, and you want to, your goal here is to maximize your like maximize the cost of the spices. So the scenario here is you're like a spice merchant and you have a limited amount of spices that you can take every day. And you want to take the maximum amount of, like, you want to be able to maximize the amount of money you can make by selling all of those spices. Okay. So again, you have a price of each spice and then you have a quantity of that spice. Okay, so does anyone have a suggested greedy solution for this? How can you maximize the amount of like dollars worth of spice you have in your bag? And the hint
You could
is,
try to take the most, the cheapest per, I guess, like cheapest, wait, maximize the cost of the spice?
yeah, you
or
want to
do like-
maximize the cost of
okay.
spices. Yeah,
Yeah, you take like the most expensive per ounce.
yeah, exactly. So the suggested solution is take the most expensive spice in terms of dollars per ounce. And by the way, it has to be maximization. Otherwise, you could just take no spices and pay $0. Okay, so that's why it's important that it's maximization. So you take the most expensive spice in terms of dollars per ounce. Okay. And until bag is full. So we'll say, without loss of generality, so here's an example where it works. Okay, so without loss of generality, it doesn't matter which of these spices is more expensive. Like in terms of like which K is more expensive. So we'll say that P sub 1 is greater than P sub 2. We're going to go to P sub 3, P sub K. So we're going to take P sub 1 until we can't take it, or we're going to take all of P sub 1 and then say all of P sub, the quantity of P sub 2, and we're going to keep doing that until we can't take any more spices. So let's say we can only take, let's say there's 5 grams of each of these spices and our bag has a quantity of 12. So we'll take 5 grams of this. We have 7 grams left. 5 grams of this. We have 2 grams left in our bag. And instead of taking all 5, we can just take 2 grams of this. Okay, and that's going to turn out to be our optimum solution. And so the suggestion to prove it is going to be a swapping argument. I like to call it a swapping argument. I don't know if they teach it in this class, but this is, I mean, I'm paid to teach you all theory. So I'm going to teach you all theory. Okay, so this is something I like to call a swapping argument. Don't expect to just call it a swapping argument on the exam. I mean, I guess you could call it that, but they should know what you're talking about. So, but the idea here, okay, with a swapping argument to prove greedy correctness is you make a, so consider an optimum solution that differs from the greedy one. So since we're trying to prove optimality of the greedy solution, this is going to be a proof by contradiction. It's going to work towards a contradiction here. And so the idea is making a swap, making any swap. Okay, so we're considering just an arbitrary, we're not imposing any restriction on this solution that we're considering, other than the fact that it's supposedly optimal and that it differs from the greedy solution. Those are the only two things we can assume about this starting point. So making any swap that goes towards greedy, that is making a swap that makes a solution look more like the greedy one. So for example, an optimum solution where we take some spice that has a lower cost per ounce, while a higher cost per ounce spice is still remaining on the table, swapping out those two quantities. Okay, that's what it means to make a swap towards the greedy solution. We're going to say that this can only increase the value of the optimum. In other words, we're showing that we have this solution, this optimum solution that's supposedly not greedy, but by making it look more like our greedy solution, we're actually increasing the value of it, and that leads to the contradiction. Okay, so what would this proof look like here? Any suggestions? Or first of all, any questions about this? Perhaps I'll explain what the proof would look like for this. So you have some spices, okay, that's in your optimum solution, but it differs from the greedy one. So you know that there exists some spice on the table that is like higher in cost per ounce than some amount of spice in your bag, okay, because it differs from the greedy solution. Otherwise, that would not be the case. Then what you could do is you could swap that more expensive price on the table, more expensive spice on the table, excuse me, with the quantity of less expensive spice that is currently in the bag, and show that that increases the cost of the bag, therefore contradicting the assumption that your bag was optimal to begin with. So again, this goes back to our moral that to prove algorithm correctness, we compare directly to the optimum. We saw how we do it using induction. This is how you do it using contradiction. And these are two kind of sledgehammers, or like for your toolbox of proving the correctness of greedy algorithms. Okay, so I will leave this for y'all as an exercise. And since I covered in discussion, I'm more than happy to talk about it in, say, office hours or just over email or Piazza or something. Okay, any questions? Okay, if not, I'm gonna stop the recording. Thanks for coming today, y'all. I still don't know if I'm gonna be feeling better by Friday, but hopefully I am, and I'm gonna get tested and make sure everything's okay, and I'll try to be in person on Friday.
Do you have a minute? I wanted to ask an unrelated question.
Yeah, sure, go ahead.
Yeah, could you just go over for like a minute on how to prove like termination